So I'm here in my garage. Just bought this new Honda CR-V. It's fun to drive up here in White Rock. But do you know what I like more than materialistic things? Knowledge. In fact, I'm more proud of this other car.
This 2002 Toyota Corolla contains an infinite amount of knowledge. When I step on the pedal, I accelerate from 0 to 60 in 12.5 seconds. Now I'll provide an in-depth explanation. As Warren Buffett once said, the more you learn, the more you earn.
Before I start with the calculations of velocity and position and time, I'd like to make some points clear. So scalar is the magnitude but has no direction, like speed or time. But vector is like a scalar, like with magnitude, but it also has direction. Some examples include velocity and position. Position is described as the vector quantity that describes a specific point relative to a reference point. And we use this to get displacement for our equation. It's final position minus initial position. Time is also used in our formula. It's final time minus initial time.
Let's talk about acceleration. Acceleration is a vector quantity which defines the increase in velocity over a period of time. In order to better understand this concept, we will take a look at the formula for acceleration and use the Toyota Corolla as an example. For instance, if the car was cruising down the highway, let's say at 73 meters per second, and it accelerated over a period of 2.5 seconds to a velocity of 95 meters per second. What is the rate of acceleration? In order to solve this, we're going to have to do a bit of math here. So first we'll look at the formula for acceleration. Acceleration is equal to the change in velocity over the change in time. We know that the final velocity of the car is 95 meters per second. And we know that the initial velocity is 73 meters per second. Now these two are both vector quantities, meaning that they have a direction. So the car is going forwards, the car is still going forwards here. Now we know that the change in time is 2.5 seconds, since the final velocity, the final time is 2.5 seconds, and the initial time is 0 seconds. So now we plug all this into the formula. So acceleration is equal to final, which is 95, minus the initial, which is 73, over the change in time. Again, final, 2.5, minus the initial. Now we have seconds here, and we have meters per second up here. So now we plug these numbers in, which gives us 22 meters per second over 2.5 seconds. This will end up with 8.8 meters per second squared. Let's say that you wanted to figure out how long it takes for the car to reach 200 meters per second forward from a standstill if the car was accelerating at 8.8 meters per second squared. To calculate this, we will modify our equation to solve for time. Time is equal to the change in velocity over the acceleration. We know that the change in velocity is 200 meters per second. And we know that the car is accelerating at 8.8 meters per second squared. By using the formula, we can determine that it will take 22.7 seconds to reach a velocity of 200 meters per second. Now, to find the change in velocity of a car, we need to rearrange the formula again to solve for delta V. Let's say that the car accelerated at 8.8 meters per second squared for 25 seconds. What is the change in velocity? So, we know that V the change in velocity is equal to the product of time and acceleration. So we know that the whole process took 25 seconds and that the car was accelerating at 8.8 meters per second squared. By calculating this, we can determine that the car's change in velocity will be 220 meters per second forwards.
So where are we going, Dennis?
We're going to the park. I have no idea what it's called, but we're going to the park.
Yeah, we're going to the park.
Kick some balls.
Yeah, we're currently walking probably to the rec center. We're gonna demonstrate the acceleration due to gravity. See you in a bit.
Look, when people kick balls, there's both acceleration and deceleration due to gravity. When your foot is touching the ball, it accelerates. However, the moment your foot leaves, the ball starts to drop.
Here we have a ball. It was just kicked by my foot at 10 meters per second. After it left my foot, gravity is now pulling it down at negative 9.8 meters per second squared. Now we want to figure out how long it will take before the ball reaches a velocity of 0 at its vertex. To determine this, we have to do a bit of math. So first of all, we know that the ball's initial velocity is 10 meters per second. We also know that we want to find out when the ball will equal 0 meters per second. Finally, we know that gravity accelerates the ball downwards at negative 0.8 meters per second squared. Using these numbers here and a formula, we can determine when the ball will reach the top of its arc. So, formula is delta t equals delta v, the change in velocity, over acceleration. Since the change in velocity is final minus initial, we just substitute these values in. So we know the final is 0, minus the initial, which is 10. And we also know the acceleration is negative 9.8 meters per second squared. This will leave us with negative 10 over negative 9.8. Now this means that it will take roughly 1.0204 seconds for the ball to reach a velocity of 0 if the initial velocity was 10. So from here, we kick the ball, it's traveling at 10 meters per second, and all throughout here, the ball is decelerating at 9.8 meters per second squared until it reaches this point here where the ball's velocity is 0, which means it's not moving. After that, the ball continues to accelerate down at 9.8 meters per second squared until it hits the ground. Now I will demonstrate what the position time and velocity time graphs look like on a kicked ball with the effects of gravity acting upon it. So first let's start off with our position time graph. Here on the y-axis we have altitude in meters, and here on our x-axis we have time in seconds. So let's say our ball starts off at 0, 0, meaning no time has passed and the ball is within your hands or on the ground. So here we have meters. And let's say 1 second has passed. And now the ball is traveling at a certain velocity and it puts it at, let's say, 2 meters in the air. Now as time goes on, the ball will slowly decelerate as the force of gravity is pulling it down until it reaches a point, right here, where the ball is stationary. This is when all the initial velocity from your foot is cancelled out by the acceleration of gravity. From this point on, the ball will continue to accelerate downwards at 9.8 meters per second squared. Now this is the position time graph for a kickball with the effects of gravity on. Now let's go over the velocity time graph for the same ball and same speed, same acceleration of gravity. Here we have the y-axis as velocity, and here we have the x-axis as time. So first, the initial velocity of the ball is 10 meters per second. Here, let's label that velocity and time. 10 meters per second for the initial velocity. And as the ball flies through the air, the effects of gravity act upon it until it reaches the top of its arc, where the velocity is 0. And then the ball starts dropping, which means the velocity will become negative as it accelerates towards the ground. And again, when it hits the ground, the velocity will drop to 0. And because the ball is kind of like an inflated, well, it is an inflated balloon, meaning that it will have some elasticity, which will cause the ball to bounce each time after it hits the ground. So we can assume that the velocity will spike up when it bounces, and it'll reach the top of its arc right here, and it'll start to fall towards the ground. When it hits the ground, the velocity will equal 0 once again, and another bounce, each time getting a bit smaller. Same routine until it just lays on the ground and the velocity is 0.
Okay, so we're going to begin our calculations with velocity, position, and time. So to do this, we do the formula, the V with the arrow equals the D with the arrow and the T. Yeah! So for our first question, imagine we're on a SkyTrain here, travels at 50 meters forwards in 9 seconds. And we're trying to find the velocity. So you take that formula I just gave you, 50 meters as the position, so 50, and 9 as the T, which is time. 50 divided by 9 is 5.5 meters per second. And because this is velocity, we're going to do 5.5 meter per second forward, because it's a vector. Now after it goes for a little while, it's going to stop and pick up some passengers. So that would take like 5 seconds for imaginary train. Then it keeps on moving, but this time it moves faster. 7 meters per second forward for 3 seconds. This time, however, we're trying to find the position. So taking the formula I gave you in the beginning, we're going to modify a little bit. So instead of velocity equals distance or position divided by time, it will be time times velocity equals position. So it would be 3, which is time, times 7 meters per second, which is our velocity. That would give you 21 meters forward, because it's still traveling forward. But then it will just let go some of the passengers for 5 seconds again, and then after that, let's say our train goes backwards, like some trains, or all trains, or sky trains, trains, yeah, trains trains, goes backwards, going at 100 meters per second. Don't worry about that alarm. If you could hear it, it's just some fire going on, not a big deal. So anyway, let's get started with our going backwards calculations. So let's say it goes at 100 meters per second on 71 meter road. So basically going backwards at 100 meters per second. And you're trying to find the time that it takes for the train to travel back to the original position. And so we're going to modify the formula a bit now. Again, so it would be position divided by velocity equals the time, the seconds. So this means 71 divided by 100 equals 0.71 seconds. So it took 0.71 seconds to travel that 71 meter of road. Now if you put on a graph, the first line will be positive, the second will be a 0 slope, the third will be a steeper positive slope, the fourth is a 0 slope again, and the last one is a negative slope.